So we want to begin this talk about spatial analysis with PostGIS and Python. Just to give some clue, who already play with PostGIS or with GIS or with spatial data before in the audience? Can you raise the hand? Yeah, some of them. Okay. This talk we will begin just at the very beginning with some really basic example and go further to complicated and more complex stuff. So at the very beginning, the first question is what is dedicated GIS system? So something is able to deal with topology and with distance between features in a database. This example is about the way the city grows up in history. For example, if you look to the river in the geography, you can see that if there is a big river, you need a bridge to cross the river, so there is a city who could grow up just beneath a big river. So if we look to which we express with PostgreSQL, it could be to look with two kind of data sets. So the first one with the cities and the second one with rivers, and to look to all the city big enough who are not close to a major river. Okay, so we want to check every outlier, every city who are big enough and who are not close to a main river to see if there is some of them who are not in this kind of pattern. And what is special here is the spatial intersect between the two kinds of geometry, the first one from the city and the second one from the river. What we get in output, so I took a dataset from France, the green points related to a city who are big enough but who are just close to a big river. But the red one are the ones who are not supposed to be there. It can be explained because they are just beneath the sea, or because something in their history. So there is something who can explain why they are not really tied to big river. I don't know because why it's blocked. So if there is something we've been a kind of motto in geography field, the connection between a kind of feature who are closed spatially. So one very usual thing we are checking with spatial geography is to look to the distance between several features. Obviously, thanks. Obviously, with distance, you can grab easily two features who are close to themselves. But what is quite neat with some quite new keyword in SQL is the ability to grab how many nearest neighbor to a feature we want at once. And this is because this keyword lateral and because this nearest neighbor operator, and with the two together you are able to grab at once how many nearest neighbor you want in a single query with quite decent performances. Other kind of thing we also want to to perform with a feature and with distance is to cluster them. So the first attempt is to retrieve the nearest neighbor, but the other one, if you got a data set with a lot of points, and you want to create some clusters, some patches, with them tied together, and there is a quite new function called cluster within, and you can, with this kind of function, create cluster, here, the purple circles, who tied your initial point data set in a few cluster. The kind of use case is related to the ability to gather some small district area into big one on this use case. If we want to play with more spatial advances PostGIS function, there is also some function related to the ability to discover if two features are or not really the same. So here you can see the blue one and beneath a green one. They are really close. It's because one is built from the other, but it could be because this is two different data sets representing the same feature, but not exactly the same. And with other distance, here, you can check how similar two features to geometry are or not. And the result is in the output is a float. So it's really handled them as a distance. Another interesting function is several noise. So it's well known in spatial analysis. The use case is from a point data set, the ability to create polygonized surfaces area where every kind of cell is just close to the other. So there is nothing, no hole between every cell, and the input data set is only the points. So the area grows as much as it can, as since they met the other cells, and so they stop. It's a quite easy way from a point data set to create an area of interest. If we want to play with 3D and not only with 2D, in PostGIS there is also some primitives like intersection, differences, and so on. And this function tied with SFC Gold extension in PostGIS are able to deal with some basic topology operation, but in 3D and not only on 2D. Obviously, in PostGIS there is more than 200 or 300 functions built in right now, but sometimes we want more, we want to go further. And at this point, one really convenient way to do that is to use Python to do so. And here there is a quite simple example with the ability to perform a geocoder function built upon Python. So the first thing to do is to add the extension, and then to create the function inside PostGIS. We want to act as a binding between the Python code here there and the SQL code itself. So here there is a few lines in Python. We are able to deal with the geocode itself. In input, it took a name, in fact an address, and as an output, it will output a geometry point related to the geocode, the point geocode. And if we call it with an address as an output, we've got here the resulting GeoJSON coordinate, and if we use this coordinate on a map, we can see there is a match between the address and the output. So with a few lines of Python and PL Python binding in SQL, you are able to perform some nice things. But the question is always how to go still behind. If we want to play more, there is a quite interesting toolbox based on Python data science stack. And if we tie this stack with Postgre and with all the GIS function in Postgre, there is a quite interesting thing to do. But the first issue is to be able to bridge the different data type. In Postgre, there is obviously PostGIS and Postgre data type, and you are also meeting WTT raster data type. So I don't know if you already know well WTT raster. It's a kind of data type able to handle raster, so it's a kind of grid, but with as many bands as you want, so you could look at it as a cube of data. And on the other side, in Python stack, the common data are based on NumPy or on the data frame with just some kind of NumPy array with a metadata in addition. So if we want to use some function provided by the data science stack, like for example one called SkyPySignal, able to deal with the difference in phases between the two data sets, it's as easy as call the Python code with an embedding in SQL. But the key point is how to do that also with PostGIS type, and to switch it, to convert it between WKB raster and NumPy array. There is a Python extension called WKB raster provided on this GitHub website, and if we called it so WKB raster, and if here we grab some geometry and convert them to raster. So we grab some vectorial feature. Here it's from OpenStreetMap, so we grab only the main motorway roads. We grab them on the wool area, and we convert them to a grid as raster with X and Y coordinates. And since we've done that, we convert the raster to a binary serialization, and this binary serialization is able to be handled by read WKB raster itself. And as an output, we grab the ND array for the first band and are able in Python to map it, for example, with matplotlib. So it's a kind of bridge between the WTB raster inside PostGIS and all the NumPy arrays in Python. On the same way, if we want to bridge this time the Postgre data type, we can use pandas who do the trick. So if we create a request here, we can retrieve quite easily by a read SQL query in pandas the data frame or the NumPy dataset. But it's slow. Using pandas is quite slow, and if you want to do quite the same but with decent performances, if your dataset is quite bigger, there is something additional called Warp Prism. The performances are this time are really good, but the query itself can only be sent as a whole table or with SQL Alchemy filtering. So there is no way at this time to put a plain SQL query. So it's something annoying, but the performances are really good. So upon your use case, you can use either pandas with all the flexibility of a custom SQL query, or Warp Prism if you want performances, but only on a whole table or on the filtering based on an array B. And obviously, if we want to do that also with the geometry, the PostGIS geometry, so here this is the example with Warp Prism. And if we want to do that with the geometry, there is Open Pandas, GeoPandas with some kind of additional support for geometry in pandas, and you can retrieve GeoData frame from a direct queries here based to PostGIS. So here, this is the output as a WTT, and here the result plot directly through matplotlib. And you can obviously do something a bit nicer as an output result. If we took an example through a geospatial time theory, here I took a dataset from Paris Open Data website, and they provide some kind of IoT sensor put on different places, and here there is several of them on a dedicated place in Paris. This kind of data a kind of measure about the road traffic, and obviously at night there is not a lot of people around this place, but obviously in some moments of the day there is more people. So if we look at the whole data set, there is a lot of high peak and low peak, and there is some error measurements also we can identify at the first representation. Once we identify this error in inputs, we can through a window SQL query grab the real moments when this error happens, because here we grab the value 0 since we've got at least 20 measurements in time were equal to 0. So since the current row and the 20 who followed are equal to 0, then we decide that's the beginning of the moment that the input measurements begin to fail. And the result output gives us the moment here when the time series is not anymore to be considered as safe in these measurements till the next moment. What can we do now with this kind of time series put in the space? We can use some extra tools to analyze what kind of periodicity we can find in the data. So once we've got the data frame, and here you've seen it was as easily to put the request and to retrieve the data set. We can launch the analysis and retrieve the trend. So there is a trend who declined on the different weeks, the monthly, periodic, and the same on the daily and on the weekly basis. So this one is more interesting because we can see that the low part of the curve is about something like 4 in the morning, and the high peak is in the afternoon. And there is also an effect on the Monday with a low peak, and on the Friday and Saturday, that's the moment where there is a bigger traffic on it. So it's a quite easy way to retrieve with few lines of SQL, few lines of Python, some interesting information about what we can find in our data. One other kind of use case we can only dream a few years ago is based on the images analysis pattern. And as I said, we can in PostGIS put some raster data in it. So by raster data we can imagine obviously grid data, but it can be also images. And there is already some kind of works related to be able to transform some aerial images. It can be from satellites or for drones or from anything we fly. And the point is to be able to train this model to be able to predict as an output what is able to recognize on the image. So the ground truth, what really is on the ground, if we class it in a few places, for example with the buildings in violet, with the vegetation in green, with the car in yellow. If we class it with a few places, and if we launch it, we already have the ability to begin to have the much bigger pattern recognized with this kind of model. The thing on it is that if we want to be able to do that, we have to train the model with a label dataset. Once we've got a trained model accurate enough to be able to output prediction good enough. On this use case, what did they do? They use an already trained model who are not dedicated at all on aerial imagery. The initial model is a generalistic one, able to recognize objects from the common life. So, if we want to have more performances, more accuracy than a generalistic model, we have to train with dedicate label data set. Once we've got a trained model accurate enough to do the job. There is already some tools able to perform the labeled part. And if we want to go further with the ability to put exactly what we want in the label data set, we can do that with PostGIS. So here it's a whole query with several steps in it. The first one is to create some point of interest. Is the corner of the tiles. The second one, from this corner, is to create the tiles themselves as a geometry. Then to create the same tiles with the same bounding box, but as a raster. Then to create the label with the really same bounding box than the tile we just create. Then to grab the image with also the same output, and then to grab the two of them, both the images and the label, even if the label is empty. At the very end, what we got is the images here in first color and the label we just create. And as it's really customized, we can here, for instance, modify as much as we want the different kind of parameters to retrieve something quite different in the label, and so to improve our training and our model. Right now with PostGIS, we already got something which by design is able to deal with geometry, with raster, with 3D. I didn't talk about LiDAR, but it's already the case also. The whole toolbox is something huge. There is there is more than 100 functions already available on it. If you want to open it up and to add some extra function, you've seen it's quite easy through Python. And the whole Python data science stack is also something huge. And we already have some way to tie them, to bridge them, even if there is several ways to improve it, mainly about performances, and also with an out-of-the-box and packaging can be, again, improved in the future. Thanks a lot.
Спасибо, Оливье.